moment generating function, MGF. So an MGF is unique to a distribution in the sense no two distributions will share an MGF. So if you have an MGF of a certain form, it has to be that particular distribution. And obviously, it generates moments. Some good ones, some bad ones, some memorable ones. He got it. No, we're not talking about that. The first moment, the second, the third, and so forth. And do keep in mind that when we talk about moments, we always talk about the theoretical ones. Of course, last time I showed you the sample moments and how we can compute sample moments if you have a sample. So it has a lot of other applications, and I'll do one here later. So what is a moment generating function? I'll call it as m sub x of t. But you do have to look in the textbook to see as to what the notation is. Nothing complicated at all. It's simply expectation of e raised xt. Good. In terms of a Taylor series, what is e raised xt? In terms of what? A Taylor series.
What's the word? 1 plus xt plus.
Keep going with time.
X to the x. I know the bottom is n factorial. Xt squared. And then 3 and 2 factorial.
Of course, we don't need all of that. Plus the dot. Did we take calculus too? I did do this at the very end, Joe. Remember?
I remember that you did it.
Yeah, Taylor series. So linearity of expectation, you just distribute the expectation in. So expectation of 1, expectation of x times t, expectation of x squared t squared divided by 2 factorial, x cubed t cubed divided by 3 factorial, and I'm going to stop with that because we don't need more than 4 moments. 4 is plenty. 1 is a constant, so expectation of a constant, it's the constant itself. So 1 plus. I have x multiplied by t. T is a constant, so I can pull t out. So t times expectation of x. T squared over 2 factorial. Likewise, t cubed divided by 3 factorial. And it keeps on going. So it doesn't matter what random variable we have, we can expand it and write it that way. Good. You can notice that I have the first moment here, the second, the third, the fourth. So what should we do to get each of those moments? Any guesses? How about the first derivative? What happens to the 1? 0 plus expectation of x. The derivative is with respect to t. So d mx of, oh, too bad he died. dmx. Dmx of t over dt, 2t over 2 factorial. Yes. If I take the derivative, that's what I would get. And what should I do just to retain expectation of x?
Make t 0.
Make t 0. Good. How do I find the second moment? Using that. Second derivative, take the derivative of that one more time. So we know expectation of x once we evaluate it is a constant. So the derivative of that would be 0. Here I have 2 over 2 factorial, which would give us 1. So 1 derivative of t with respect to t is also 1. So we get 0 plus expectation of x squared. 3 times 2t divided by 3 factorial. Expectation of x cubed plus double. Of course, when you go up there to 3, and excuse me, 3 times 2 is 3 factorial. So 3 factorial and 3 factorial would get cancelled, and you are ready for the next step when you get to the third derivative. But regardless, if I want to find the second moment, all I have to do is plug in 0 in the second derivative. I will get expectation of x squared. In general, the nth moment expectation of x raised n is simply equal to nth derivative of the moment generating function evaluated at
0.
Good. Yes. Hence the name moment generating function. It generates moments. There's another thing called probability generating function, which helps us generate probabilities. But I'm not going to do that in this class. We need to move on to joint distributions. Any questions here? Okay. Here's an example. I will do 2 and I'll let you do 1. Bernoulli P. If X is Bernoulli with parameter P, what is its PMF? Finding the moment generating function of a Bernoulli is easy. So we've got to sum over the possibilities. Expectation of xt multiplied by probability of x is equal to k. When, in this case, the just in case it. Correct, we're evaluating x. So when k equals 0, what do we have? Yes.
I don't know if this is related. This is basically just a Fourier transform. Like,
You know, I'm glad you caught that. Yes, it is.
okay.
It is very much related to a Fourier transform, and to be very specific, it goes from this to a Laplace transform to Fourier transform. If we evaluate it at a specific complex value, it simply is Fourier transform. Okay. So when k is 0, what do we get? E raised 0 times the probability of x is equal to 0. Yes. And then k is equal to 1, I will have e raised to multiplied by the probability of x is equal to 1, which is, we'll get to that in a bit. E raised 0, 1. Probability of x is 0 is p. Plus,
Or 1.
thank you, 1 minus p. Someone's paying attention. So e raised t multiplied by the probability of x is equal to 1, which is simple. P. Good. So I've got a p in common, so it simply have that. Yes? So that is the moment generating function of a Bernoulli, and of course T has a zero to infinity. I can't find the expectation using the moment generating function. What is the expectation of a Bernoulli bounded variable? P. So the first derivative of the moment generating function, the derivative of 1 is 0. P times e raised t, derivative of e raised t with respect to t is p e raised t. P times -1, derivative of negative p is just 0. So we will have p e raised t. And as I plug in 0, p multiplied by e raised 0, I get p. Just to add, Nathan, once we move this to the complex domain, it is called the characteristic function.
Okay.
Good. Move on. What is the second moment? It is not 0. It is a common mistake where someone would simply put it as 0 because they look at the previous value and say, oh, that's a constant, so derivative of that must be 0. But we are not taking the derivative of that, rather we're taking the derivative of the function. So I end up getting p e raised t. Derivative of that. If I evaluate it at 0, t equals 0, I end up getting p. Good.
So is every moment just gonna be the same?
What do you mean?
As it's,
Past that point, yeah.
yeah.
Well,
I mean, keep taking derivatives, it's just gonna be p, the t.
right, exactly. Well, here is a problem. That's not the variance. The variance of the binomial is p times 1 minus p. Not the wrong answer.
Right, the variance is the second moment.
The variance is not the second moment. So the variance of x is actually the second moment minus the first moment squared. So p minus p squared, we get p times 1 minus p.